Gurney flaps are incredible flow control devices. They are literally just these little plates pointing vertically down at the trailing edge of a wing, like we see here in figure 1b, coming down here. They are often put onto uncambered wings, and they make the wing perform more like a cambered wing, so you produce a little bit of lift at 0-degree angle tack. And in other podcasts, I've talked about just how amazed I am at them because they are so small, but they can increase the wing's lift by like 10% or even more. But as I mentioned, they are sometimes put on uncambered wings. So what would happen if you put them onto cambered wings? Would they still be effective at increasing the lift still? And in addition to Gurney flaps, there is a relatively new type of flow control device that some people call vortex generators. They aren't actually vortex generators in the traditional sense, but their effects on wings are being looked into. And in fact, I myself was actually looking into this about a decade ago, researching this flow control device. Anyway, their purpose is to delay stall. So there is a chance that a Gurney flap will coexist with this new type of vortex generator. As such, how would a Gurney flap perform with this upstream disturbance from the vortex generator? Would they still perform as well as if they didn't have them? Or would they perform better or about the same? Well, that is what we are focusing on today. How do Gurney flaps affect a cambered wing? And do Gurney flaps with these new vortex generator-like devices play nice together? So to look at this, we're looking at a paper called Study of Epler 423 Airfoil with Gurney flap and vortex generators. So it is open access, so you can find it in the link below. So to answer these questions, these researchers conducted experiments in a wind tunnel as shown in figure 2. So let's scroll down there and look at that figure here. So this airfoil spanned the entire tunnel's cross-section, as you can see from figure 2c. And this is important to note because we will now not get any wingtip vortices affecting the flow of the wing. As such, we can conclude that the results from this study are more applicable for very large aspect ratio wings. The reason for that is because when a wing has a large aspect ratio, it means that the wing has a relatively large span and not a very large chord, relatively speaking. As such, three-dimensional effects from the wingtips don't affect the rest of the wing as much. On the other hand, if the wing had a small aspect ratio, then the wingtip vortices would play a much greater role in the wing's overall aerodynamics. So the results here are more for wings with large aspect ratios because they have this wing spanning the entire wind tunnel cross-sectional area. Now, the wind tunnel test section had a cross-sectional area of 920 millimeters by 920 millimeters, so it is a decent sized one. From what I can tell, based on their wing chord and the maximum angle that they tested at, the maximum blockage ratio was 5.1%, which is pretty good. They didn't go too high on this. They also don't talk about correction factors, but below 3%, you usually don't need to have them anyway. So at the very least, most of their results are generally fine without any correction factors. Also, they don't give us the turbulence intensity level, but they do say that the air travels through a honeycomb, which then straightens it, and as you'd expect, and then through 4 mesh screens of various sizes. From the general description here, we can ballpark this tunnel's turbulence intensity to around 0.6% to 1.0%. Now, they did pressure tappings on the airfoil surface, and I went through pressure tappings in quite a bit of detail a couple of weeks ago in podcast 177. So I won't go through it too much here, but just from figure 2, it looks like they actually put the holes into the airfoil instead of using the pseudo metal surfaces I was talking about a couple of weeks ago. So they actually drilled into the surface here to install these pressure tappings. And one thing that I didn't mention back then, but I was talking with one of your amigos, Rolanda Tillett, and we were discussing in the comments that with this particular way of tapping the airfoil where you have to actually drill in, you have to be careful about making sure that there are no burrs on the edges of the holes, because these burrs can actually change the pressures that you are reading and give false results. So one way to reduce the number of burrs you get is by drilling the holes, then sanding them, and then connecting the tubes. If you don't sand the holes, then you'll likely get some burrs. Also, the direction that you drill from also changes how likely you are to get burrs. So if you drill from outside to inside the airfoil, then usually you'll get a few fewer burrs than if you drilled from inside to outside. So that's just a quick tip on how to put pressure tappings into a surface. And just quickly, if you're an aerodynamicist or fluid mechanist and want to learn OpenFoam, take a course in the link below. It takes you step by step through even how to install it and all the way to running your own DS simulations. But let's get back to this paper. So we come to something that I have never really heard of before. They say that they smoothened the surface of the airfoil with adhesive putty. So to tell you the truth, I'm not completely sure what they mean by that. I guess they mean that they spread putty onto the surface and then let it dry. If so, then I can definitely see that working, because if you apply putty to a surface and then let it dry, you'll usually get a pretty smooth surface. Now, one thing that you can do to get an even smoother surface is to sand the putty. Then it comes out really, really smooth. And then if you know the grit of the sandpaper, you can also then determine the surface roughness. So I guess they mean that they just spread putty onto the surface and then let it dry to give it a uniform roughness and a fairly low roughness as well. So another thing is that they don't actually give the Reynolds number here, but they do give the info required to calculate it. And if you do that, it comes out to be about 270,000, which, coupling that with the general intensity of this wind tunnel and the fact that they smooth the surface with putty, means that the flow is probably transitional. And that means that they might be getting a laminar separation bubble. They actually give pressure coefficient data later over the airfoil, so we can actually tell from that later on if bubbles did form, but we'll cover that in a little bit. So first, the airfoil used was an Epler 423, which is a fairly common and basic airfoil. It has a maximum thickness of 12.5%, so middle of the range, and that occurs at about 23.7% of the core, so a lot like regular NACA 4 series airfoils. It has quite a lot of camber though, coming in at 9.5% of the chord, and that maximum camber is occurring way back at 41.4% of the chord, so almost halfway, so it's quite fat in the middle. So at this general Reynolds number, online data says that the maximum lift coefficient should be about 2.0, which is really high, and the minimum drag coefficient should be about 0.02, which is also a little high. The stall angle attack is about 12 degrees, and the stall is a little gradual. So it's definitely not sudden, you don't get this massive drop, but it's not really gradual, it's in between. So in figure 3, we see pictures of the airfoils tested, and they're interesting. So on the left, we see the pressure side of this airfoil, so underneath, and at the back, we have the Gurney flaps at the top of the picture here. But now on the right, we see the wing with the suction surface pointing up, so we can look looking down on the top of the surface. And this time, what the authors call vortex generators are attached to the leading edge. You can see these like points coming out of the leading edge. This is a little bit of a misnomer in my opinion. I mean, the device that they are calling a vortex generator is literally just peaks coming out of the leading edge. Now, they are much more similar to things called tubercles, which I have actually spent some years researching. So calling these vortex generators isn't quite accurate because a typical vortex generator is located somewhere on the surface of the airfoil. These are located at the leading edge and they protrude forward. So that is one difference, and it might seem trivial, but that difference in flow that results in different flow physics is actually quite important. So with this particular flow control device, when it is just protuberances from the leading edge like this, yes, they do create counter-rotating vortices that travel downstream of the airfoil's chord, but the strength of the vortices is greatly affected by the airfoil's angle of attack. So at 0 degrees, typically no vortices are created at all. Contrasting that with traditional vortex generators, which are objects on the surface, it doesn't really matter what angle of attack you're at, as long as you have some flow hitting it, vortices will form. So that is one difference between this particular flow control device and traditional vortex generators. It means that at 0 degree angle attacks, these vortex generators, as these authors are saying, don't actually produce vortices, whereas traditional ones do. Another important distinction is that the vortices created by these protuberances start from the surface of the airfoil, and then they grow into the rest of the boundary layer and even into the free stream flow. Conversely, traditional vortex generators create vortices away from the surface, and then they grow and start to reach the lower regions of the boundary layer. So the flow physics is off there. That means that depending on which configuration you have, either these protuberances or the vortex generator will behave differently in terms of mixing the high momentum fluid into the boundary layer and delaying stall. One may be more efficient than the other, and I know which one is more efficient. It's these protuberances compared to the vortex generators. So another important difference is that these protuberances, as they are here, change the airfoil profile as you go along the chord from the wing root to the wing's tip, because the chord changes periodically when you go from the trough to the peak. When you go from the trough, obviously the airfoil gets longer, the chord, as you go to the peak, if you go to the trough, then it gets shorter. So this changes the airfoil profile, which means that the relative thickness and camber also change, hence affecting the stall pattern. So traditional vortex generators don't change the airfoil profile like that. Hence, their effects on stall come purely from the vortices and not from modifying the airfoil profile. In this particular case, the airfoil profile is being modified, which also will change the airfoil performance. So from all of this device that the authors here have is not really a vortex generator. So yes, they do create vortices, but the objects that are termed vortex generators are typically used for quite a different style of object, and they perform quite differently than what we have here. These protuberances are more like tubercles, and they do behave like traditional vortex generators to some extent, but then they have their own particular quirks that make them different. So these vortex generators, as the authors call them, had a length of 2.5% of the chord, and the leading edge featured 9 of them, which were spaced evenly at 2% of the chord increments. So in table 2, they give the different combinations of these vortex generators and Gurney flaps tested. They call them vortex generators. I'm going to call them tubercles. If you hear either one, then you really know what I'm talking about here, just for this particular paper. So in table 2, if we scroll down, here we go. So the vortex generators, and I say that term, as I mentioned, just to keep consistent with the authors. Anyway, these vortex generators stay at a constant geometry, but the Gurney flap changes from having a length of 2% of the chord, so literally just 2%, it's really tiny, all the way to 5% of the chord, which is now quite a sizable flap just coming down. They tested this range of Gurney flap sizes with and without vortex generators, these tubercle things, and from -4 degrees to 14-degree angle attacks. So let's jump into the results now. So they give a lot of pressure coefficient distributions, but let's first look at the lift and drag coefficients overall, because that gives us a good overall view of how well the Gurney flap is affecting the airfoil with and without vortex generators as well. So in figure 15, let's scroll down to that one. This is figure, okay, we've got a long way to go. Figure 15 is down here. Okay, here we go. So we see the effect of just different sized Gurney flaps compared to the clean wing, which is the blue line here. So immediately it is obvious that pretty much any size of the Gurney flap greatly increases the lift coefficient at pre-stall angle of attack. For example, at 0 degrees, the clean airfoil is producing a lift coefficient of about 1.2. With even the smallest Gurney flap of 2% chord, the lift coefficient is now 1.75, so a 45% increase just with a tiny Gurney flap. What's more, increasing the Gurney flap size does increase the lift coefficient further, but not by much. I mean, like the 4% Gurney flap is producing just as much lift as the 5% Gurney flap. So that shows the Gurney flap here is definitely producing more lift, but you don't really need a big one to reap most of the benefits. In fact, increasing that size sort of results in this point of diminishing returns. Looking at figure 17, we see the drag coefficient with just the Gurney flap, and very interestingly, the Gurney flaps don't increase the drag coefficient at low angles of attack. That's really surprising. I mean, you literally have like this vertical sheet coming down, and that doesn't affect the drag coefficient much at all. So that means that you can pretty much get a 45% or higher increase in lift coefficient without a drag penalty. That's insane. That's like if you could go out and watch the game with the boys, then come home and you don't get any fall from your girlfriend. That's just the jackpot. So anyway, I should say that I'm not that confident with the drag coefficient plots because I can see that the lines wiggle around a little from the angle attack to angle attack when they should be really more smooth. So I think that perhaps there is some error in the system that isn't being accounted for here. Well, either way, the drag coefficients seem about the same, so we can take that with a grain of salt. Now at post-stall angles of attack, the clean airfoil seems to perform much better than most of the Gurney flap configurations for the drag coefficient, which brings me back to thinking that there is some error in the drag measurements that isn't being accounted for here. Now, what about the effects of having these vortex generator things on the front of the Gurney flap? Well, in figure 6, we see the effects on the lift coefficient, and immediately the effects of these so-called vortex generators are more similar to what we see with tubercles. That is that the stall is far more gradual and even non-existent to some extent. As for the combination with the Gurney flap with the vortex generators, these tubercle things, again, the addition of the Gurney flap results in far better lift coefficients. For example, at 0 degrees with the Gurney, without the Gurney flap, the lift coefficient is about 1.0, so this is just with the tubercle things. With the small Gurney flap, the lift coefficient now shoots up to 1.5, so a 50% increase, as we saw when we were just looking at the Gurney flap without vortex generators in figure 15. And once again, yes, increasing the Gurney flap size does increase the lift coefficient, but the larger it gets, the smaller the additional benefit becomes. So again, you're reaping most of the lift coefficient benefits with just a small Gurney flap. Now, comparing figures 15 and 16, we can see how the vortex generators affected the lift coefficient. So the blue lines are for without a Gurney flap, and the vortex generator, the tubercle things, reduced the lift coefficient by about 20% in this case. So that's quite a lot. From my research, what I've seen in other research, tubercles usually drop the lift coefficient by about 5 to 10%, but 20% is a huge hit to the soft ones. So moving on to the drag coefficient in figure 18, we see that the Gurney flap now increases the drag coefficient a little bit across really the entire angle attack range. So that increases about 10 to 15%. Interestingly, the size of the Gurney flap doesn't affect the increase much at all. Like literally, you get that increase even with the smallest Gurney flap of 2%. So in for a penny, in for a pound kind of thing. It doesn't matter if you have a bigger one, the drag coefficient is going to be about the same. So comparing the effects of just the vortex generators without the Gurney flap, so the blue lines in figures 17 and 18, we see that the vortex generators reduce the drag a little at lungs attack. I would say by about 5 or 10%. And this is actually what I also found when researching tubercles, so it makes sense here too. I concluded that it was partly from an induced drag reduction, but also from a pressure drag reduction too. Now in figure 19, we have the lift to drag ratio of the wing with and without a Gurney flap. So overwhelmingly, the addition of the Gurney flap improves the lift to drag ratio. We're seeing around a 50% increase, which is awesome. And for when we have the Gurney flap and vortex generators, we see in figure 20 that still the addition of the Gurney flap does generally increase the lift to drag ratio, but it isn't by as much. And even at some angles of attack, not having a Gurney flap might be better. So comparing just vortex generators, so the blue lines in figures 19 and 20, the addition of the vortex generators greatly reduced the lift to drag ratio by about 40% on average, which is mostly from the massive lift coefficient drop we saw earlier from these tubercles. So this is not what I found when I researched tubercles actually. I found that for the setup that I had, that the tubercles increased the lift to drag ratio by like about 10%, but then my designs are a little more in depth than the simplified ones. And the results I found were also found by some other researchers, so it really depends on the geometry of the tubercles. Now, let's look at the overall effect. That we've looked at the overall effects of the Gurney flaps and vortex generators. Let's look at a deeper dive on the pressure coefficient distributions over the airfoils with these flow control devices. So in figure 6, for example, let's scroll up there. That's figure 9. Got a bit more to go. There are a lot of figures in this paper. Here we go, figure 6. Let me zoom out a little bit. So in figure 6, we see the effects of the 2% chord Gurney flap on the pressure coefficient distribution over the airfoil. And figure 6a is for the clean wing and figure 6b is for the Gurney flap wing. It's a little bit hard to compare them because they're on 2 different pages, but let's try our best here. Okay, here we go. So remember that the Gurney flap pretty much always increases the lift coefficient by a lot, and the pressure distributions we are seeing here back that trend up. I say that because we can see that when the Gurney flap is present, the minimum pressure coefficient seen over the airfoil drops by about 20%. So this lower figure here, you can see that like the minimum pressure coefficient is like minus 3.5 compared to about minus 3 or so. So that makes sense that the lift coefficient is increasing because we can see in this pressure coefficient distribution that is what is happening. So in addition to that, we can see that for both the clean wing and the Gurney flap wing, there seems to be a laminar separation bubble. And I can tell that because if you look at the bottom lines of each figure, so these bottom lines here and these bottom lines here, there is a region from about 20% of the chord to about 50% of the chord where the lines kind of plateau a little bit. That is a strong indication of a laminar separation bubble. And given the Reynolds number of this airfoil and the ballpark turbulence intensity, it makes sense that there is one here. In fact, if there wasn't one, that would be more surprising. So in terms of how the Gurney flap affects this bubble, well, it doesn't really seem to affect it too much. If anything, I would say that there might be a slight reduction of its severity because the lines don't plateau as much, but that could very well be the error and also me just eyeballing it. So I think it's safe to say that the Gurney flap doesn't really affect the bubble too much here. In terms of the lower surface, so these upper lines here, the Gurney flap doesn't seem to affect the pressure distribution here much at all, and I'm actually struggling to find any real differences between them. So I think that at least 2% chord, the Gurney flap only really affects the suction surface. What about when the Gurney flap gets bigger, like 3% and 5%? So in figure 7, we see the pressure coefficient plots for these situations. So figure 7 here. So again, it is a little hard to compare them, but from what I can tell, increasing the Gurney flap size, it seems to just slightly drop the pressure coefficient on the suction surface, which would agree with what we saw in terms of the general lift coefficient trends, where increasing the Gurney flap size did come with additional lift coefficient benefits, but it was marginal. Now, we're also interested in how these tubercles affected the pressure coefficient distributions. And if you are familiar with how tubercles work, then what we're about to cover will come at no surprise. So in figure 11 and figure 12, so where are these ones? Here we go, figures 11 and figure 12. We see the pressure coefficient distributions with and without tubercles from 8 degrees to 14 degrees. So 8, 10, 12, and 14. So this angle attack range is important because this is where tubercles really shine. They delay stall and soften it greatly. And they do that by mixing high momentum fluid into the lower regions of the boundary layer, like traditional vortex generators do. And at a low angle attack, like 8 degrees, as we see in figure 11a here, there isn't too much of a difference on the suction surface as we approach the trailing edge, so around here. In fact, the tubercles do affect the suction surface pressure distribution, but it's more on the first half of the airfoil. And here they reduce the pressure coefficient, which results in the drop in lift we saw earlier. And that lines up with the lift coefficients we saw before. Now, going to high angles attack, like 14 degrees in figure 12b, so this figure here, we start to see what tubercles really do. So the first bit of the airfoil, the tubercles reduce the pressure coefficient, so around here, on the suction surface. But once we hit around 35% of the chord, the airfoil without tubercles starts to increase in pressure, so there's a massive stall here. From figure 15, we see that the lift coefficient is dropping here, and you'd expect the stall to occur, as we do see, so that all lines up nicely. But when you have the tubercles added, so this blue line, all of a sudden the pressure coefficient over the suction surface stays low and gently trends back to 0. That means that the flow is attached and the airfoil is still producing lift. And that completely agrees with what we saw in figure 16 if we scroll down here. Figure 16 shows that even at these high angles attack, the tubercles do preserve lift. So that all makes sense. What's more, this completely agrees with tubercle literature. Tubercles delay stall and make the stall pattern softer, so you don't get this sudden drop in lift. So that all makes complete sense, what we've been seeing here in terms of the effects of these tubercles and the effects of the Gurney flaps. And kind of when you put them together, they're kind of independent of each other. So with that, we come to the end of this podcast. It was cool. We saw that Gurney flaps are incredibly beneficial to even high cambered wings. And the Gurney flaps don't really even need to be that big. Like even 2% is enough to make a massive difference to the lift and like increase the lift to drag ratio by like 40 or 50%. That's a huge increase in the efficiency. We also saw some vortex generators, which more specifically are tubercles, and how they benefit the wing at high angle attack. So if you like this podcast, make sure to hit the like button and the subscribe or follow button, whichever platform you're on. And we were talking about experiments in this podcast. And did you know that most researchers don't take into account changes in the density of air in their experiments? This poses a problem because it introduces a 2 to 4% error in the data just on a regular day. And this error grows even greater between seasons. So to get rid of that error, we made the atmosphere hawk, which you can find in the link below, along with the math showing you how the density of air changes and how that really affects your results and why you really need to take into account these changes. Also, if you want to learn OpenFOAM, which is a really powerful CFD software, but hard to learn, take our course in the link below. It takes you through from the very basics, like even installing it, all the way to running your own DAS simulation. And you can put in whatever you like. And we are actually also just about to release an advanced meshing course for OpenFOAM. It's very advanced. It goes all the way to like overset meshes and even dynamically deforming meshes. So if you want to learn how to do that and get really good at OpenFOAM and even just that CFD in general and learn some things that most don't, so you have a leg up in work, get that course and learn how to do that. And it will be out in like 2 weeks, so keep your eyes peeled for that. So with that, we come to the end of this podcast. Peace out, amigos.